Hello everyone, my name is Divine Seed. My topic today is RISC-V. I'm going to talk about it in a very practical way, not just as a buzzword, but as a real CPU architecture that shows up in our industry, in our laptops, and even in our space systems. I'll explain what RISC-V is, why it matters that it is open, and what kind of products and systems are already using it. By the end, you should have a clear mental picture of RISC-V as a flexible platform, not just as another CPU. So here is our roadmap. We're first going to quickly define what an instruction set architecture is, also known as a ISA, because that is key behind the idea of RISC-V. Then I will show you why RISC-V differs. It's modular, so you can build only what you need. After that, we'll connect the mental design to real-world impact, such as cost, customization, and transparency. Then I'll share a few adoption signals from the industry, such as NASA case studies, and a quick look at early customer laptops. I will finish with the challenges and the practical takeaway, what you should actually remember. Think of a computer as three layers. At the top is software, your apps, the operating system, the compiler. At the bottom is the hardware, the CPU, the microarchitecture, the cache, the pipeline, and all the physical implementation details. In the middle, which is the most important, is the ISA. And the ISA is basically the contrast between the hardware and software. It says these are the instructions the CPU understands, and this is how they behave. RISC-V is a free and open ISA. That means that the rules are public, royalty-free, and designed to be extended. It started at UC Berkeley and later moved into into industry governance to keep the specs stable and widely usable. So the mental model is the contract stays stable, but implementation can vary. This slide shows the big design idea. RISC-V is modular by default. There is a small base ISA. Think of it as the minimal set of instructions for a working CPU. Then you can add standard extensions depending on what you need. For example, M adds multiplication, adds atomic operations for accuracy, F and D are floating points, and C compresses instructions to save code space, and V adds vector operations for data parallel work. And if a company has a specialized workload, they can also add custom extensions without throwing away compatibility. So instead of one fixed vendor logged ISA, it's more like Legos blocks. The engineering takeaway is hardware, software co-design. Tune the ISA to the workload, then tunes compiler and libraries to match. Now, why does open actually matter? Because it changes real engineering decisions. First, cost and constraints. A royalty-free ISA reduces licensing friction and lowers barriers for new chip teams. Secondly, customization without breaking everything. You can extend the ISA while keeping standard foundations. Third, transparency. Open specs makes it easier to inspect and reason about what the processor is supposed to do. Useful for security and verification, and actually ecosystem diversity. Multiple implementation reduces vendor lock-in. So, in practice, open plus modular turns RISC-V into a platform for specialized chips, not a one-size-fits-all winner. If you can't change the contract, you can you can't fully tailor the system. RISC-V gives a legal and technical way to tailor it. Let's take a look at adoption signals. Basically, where RISC-V is showing up in the real world. One major example is NVIDIA. Industries reports that NVIDIA's estimate shipping around 1 billion RISC-V cores inside their GPUs in 2024. Not as a main CPU you program directly, but as internal control cores that handle many system functions. In automations, Infineon has publicly discussed adoption of RISC-V, largely because cost pressure is intense and the architecture is flexible, and Meta has been reported using RISC-V in AI accelerator cards. Again, often in control and integration roles. The pattern is important. RISCV is already common as the brain behind the scene. In larger systems, and it's expanding upward from here. Here is a high stakes study. NASA next generation high performing space flight computer processor, or HPSC. NASA selects Sci-Fi's RISCV IP as a core CPU component for HPSC, and the announcement describes huge performance goals on orders of 100 times the compute capabilities of prior space computers. Supporting things like automation, rovers, vision processing, guides, and communication. Why is this important? This is simple. Space systems demand reliability, long life cycles, and stable tool chains. NASA's choice is a strong vote of confidence that RISCV ecosystem can trust and maintain for system critical use. Now let's talk about laptops because there is where RISCV starts. It feels real to everyday users. IEEE Spectrum reports that in 2025, RISCV laptops were becoming accessible enough for early adopters and developers, including the idea of modular computer systems, which pretty much means that you can change the different components. And with these modular systems, the RISCV mainboard can exist alongside with the x86 board. A concrete example is deep computing. They sell a full RISCV laptops called DC Roma laptops. Two, builds around a RISCV SoC and paired with mainstream Lexus options. The message isn't that RISCV laptops aren't instantly mainstream. The message is that the hardware from factor is here. The openness plus the modular hardware that makes implementation practical. To keep it realistic, there are challenges. First, ecosystems maturity varies by domain. Tooling and software stacks are stronger in areas than others. Secondly, in the industry, like automation, like automotive, reliability and certification are real concern because there isn't single vendors to blame if something fails. Third, for AI workloads, specifically control CPU, whether it is RISC-V ARMS or x86, usually still needs a dedicated accelerator for metrics or tension work. And finally, compatibility takes time. Compilers, operating systems, and libraries have to be turned and validated. So, the practical takeaway is treat RISC-V as a platform for specialized design and learning. It won't replace everything overnight, but it enables new design where openness, tailoring, and long-term control are worth it. And here's the resources that I got these from. Here are the headings and here are the various websites. If you want to check it out, you can look at any of these resources.